Hello, welcome to the FiberCell Systems mini webinar, Beyond 3D, Recapitulating Nature with a Hollow Fiber Bioreactor. I'm John Cadwell. Hollow Fiber Bioreactors represent a three-dimensional platform for the recapitulation of complex in vivo biological systems. High cell densities permit the cells to modulate their microenvironment and enhance cell-to-cell interactions. A hollow fiber bioreactor is a tool that permits a large enough number of cells to be in close enough proximity for a long enough period of time to allow complex multicellular biological functions to fully develop. It is this additional element of time that makes a hollow fiber bioreactor a true 4D culture system. Here we have cell culture through the ages. The first attempts at culturing cells outside of the body was performed by Harrison in 1906. He was attempting to culture frog neuronal explants on plasma clots. You can see a plasma clot represents a three-dimensional cell culture support. Many years passed before cell culture became the ubiquitous technique it is today. It consists of culturing cells on non-porous two-dimensional plastic surfaces and generally in the presence of fetal bovine serum. If we want to culture more cells, we have to just have more surface area. But current two-dimensional cell culture technology is based upon the culturing of cells on non-porous two-dimensional plastic surfaces in a subconfluent state in the presence of fetal bovine serum. This is not a physiologic way to recapitulate in vivo cell culture conditions. Flask-based two-dimensional culture systems subject the cells to what we call the feast or famine cycle. Cell culture conditions are constantly changing. When we first seed the cells, it's what we call the lag phase. This is while the cells are conditioning the media, secreting some of their own cytokines to optimize their microenvironment. When the conditions are optimum, then the cells will start to consume glucose. They'll be in their optimum cell culture conditions for the recreation of proper biological functions. Here we're going to designate that as being monoclonal antibody production, but it applies to many different physiologic parameters. Just when things are getting good, it's time to split the cells and repeat the process over and over again. It is now being recognized that flask-based two-dimensional cell culture, although a useful tool over many years, does not truly represent how cells grow in the body. So, wouldn't it be nice if we had a cell culture methodology that allowed us to keep cells at their optimum cell culture conditions for extended periods of time, if we could maintain them in a homeostatic fashion? In point of fact, that's exactly what we can do with the hollow fiber bioreactor. We've cultured a hybridoma for up to a year of continuous culture. We have cultured a glioma cell line for 2 years of continuous culture in the same hollow fiber cartridge. Hollow fibers are tiny filters shaped like drinking straws, about 200 microns in diameter. We can control the pore size of these filters anywhere from 5,000 Daltons up to 0.1 microns. So a hollow fiber bioreactor is based upon the principle that thousands of these tiny little filters are sealed at each end with a polyurethane plug at the end of the cartridge, so that anything that goes to the end of the cartridge necessarily goes to the insides of the fiber. Typically, we culture the cells on the outside of the fiber. So what we've done is set up a semi-permeable barrier of defined molecular weight cutoff between where the media is flowing and the cells are growing. So it's designed so that small things like nutrients and waste products, glucose and lactate, can freely cross the fiber. But larger things like cells, antibodies, viruses, extracellular vesicles, etc., cannot. So they'll become concentrated in the area outside the fibers. The other thing about hollow fiber bioreactors, they allow cells to grow at extremely high densities. So it's the molecular weight cutoff of the fiber can concentrate conditioning factors around the cells and allow them to optimize their own cellular microenvironment. Hollow fiber bioreactors are fundamentally different from two-dimensional flask culture in 3 fundamental ways. First off, they have an extremely high surface area to volume ratio. Our C2011 cartridge has 4,000 square centimeters of surface area and a volume of 20 mils. We have 200 square centimeters of surface area per milliliter volume. So you have to imagine a film 50 microns thick. Extremely high surface area to volume ratio is what permits us to grow cells at extremely high densities. Typically, we can culture cells at 1 to 2 times 10 to the 8 cells per mil. This is the only way that I know of that we can culture cells at in vivo-like cell densities, tissue-like densities. Secondly, cells are bound to a porous support, not a non-porous two-dimensional flask. The reason that we have to keep cells in a subconfluent monolayer culture in flask culture is because in flask culture, the nutrients come from the top down. So when cells pile up on top of one another, the bottom layer of cells don't get nutrients and oxygen, so they die, peel off, and float away. In the hollow fiber bioreactor, the nutrients come from the bottom up. So we never have to split the cells. Passage number is irrelevant, and they're free to grow in three-dimensional multiple layers. Lastly, we control the molecular weight cutoff of the fiber, so we can control the cell microenvironment by retaining growth factors, and we can concentrate secreted products and enhance cell-to-cell interactions. Keep in mind that a Dalton is the mass of a hydrogen atom, and an amino acid, average molecular weight is around 120. So we can put this into perspective when we're looking at a 5,000 Dalton, 20,000 Dalton molecular weight cutoff fiber. Monoclonal antibody, IgG1, has a molecular weight of 147,000 Daltons, 147 kD, so it's about 1,200 amino acids. So the hollow fiber bioreactor is designed to work just like your body. We use a positive pressure displacement pump, works just like your heart. Squeeze on this tubing and two one-way check valves. The loop of silicone tubing is where gas exchange takes place. Media recirculates through the insides of the fiber, nutrients and waste products cross the fiber, and we can collect any secreted products out of the ECS or extracapillary space. The silicone tubing for gas exchange means the system is a sealed, closed system. It's effective for being a biosafe system and allows us to culture cells for many months or longer. This is a little diagram and cartoon. It shows how the fiber bundle is assembled and sealed in the ends. This loop of silicone tubing is where the gas exchange takes place. Here's our pump tubing. We utilize a positive pressure displacement pump or squishy pump because a peristaltic pump will shed plastic off the pump tubing. It's a friction-based pumping system, so it'll shed plastic off the pump tubing. That's called spalling. These plastic particles will clog the fibers. So this is why we want to utilize our positive pressure displacement pump, a frictionless pumping system, and we can generate flow rates up to around 180 mils per minute. So the media recirculates. FiberCell duet pump will support two independent hollow fiber bioreactor cartridges. It's designed to fit inside any standard CO2 incubator. Gas is controlled by the incubator. We use passive gas exchange across the silicone tubing. Temperature is controlled by the incubator. We have a thin cord for power. It's a low voltage brushless motor, does not generate any ozone, and is designed not to generate any additional heat inside the CO2 incubator. This is just an example of what cells look like growing in the cartridge at 1 to 2 times 10 to the 8 cells per mil. I'm going to provide a couple of examples of how 3D cell culture in a hollow fiber bioreactor is a more in vivo-like way of growing cells, and how cell culture conditions have a direct effect upon cell physiology, and then we'll move on to some of our co-culture examples. This is an example of a hexamerized IgG produced in a CHO cell. It's a hexamerized IgG, 6 IgG1 subunits held together with 3 IgA tails. It's a real Franken protein. When it's cultured in flask culture, 40% of the protein is expressed as an improperly folded monomeric subunit. The exact cells harvested out and placed into a hollow fiber cartridge. Now we have 95% plus of our protein properly expressed as an intact monomeric subunit. So we can see that the cell culture conditions have a profound effect upon cell physiology. Now, hollow fiber, we can do both suspension and adherent cell types. And my favorite example is where we can co-culture suspension cells with adherent cells, and I'll show you some of that. We do get 100%, 100 times higher concentration of our secreted product. And because of the high cell density and the cells manipulating and controlling their own microenvironment, we can easily adapt the cells to a serum-free medium. This is especially important when looking to enhance cell-to-cell interactions in the absence of serum. And here it is. This is our hexamerized IgG. The 1, 2, 3, 4, 5, 6 IgG1 subunits held together with 3 IgA tails. And what I find interesting is that this researcher has replaced the FV region of the antibody with CD4 receptor. And this is GP120 on HIV. So what he's done is use this as a backbone to make a dodecaramized CD4 receptor that cross-links HIV and inactivates it. I've always liked this because this is not a cartoon. This is an actual colorized cryo-electron micrograph. This is another example of more in vivo-like cell culture function in the hollow fiber bioreactor. This is a comparison of two-dimensional flask culture and a hollow fiber bioreactor three-dimensional culture of a cholangiocarcinoma cell line. The idea was to try and look for a circulating biomarker of protein secreted by these cells. This is a direct comparison to the flask. So if we're just concentrating the secreted product, just a more concentrated secretome, all of these proteins should be concentrated to the same degree. Instead, we see that one specific protein, NGAL, is secreted to a much higher degree in three-dimensional culture, a more physiologic environment. And as it turned out, NGAL did serve as a viable circulating biomarker for cholangiocarcinoma. So three-dimensional bioreactor cell culture is a more in vivo-like way of growing cells. This is an example of what I call asymmetric cell co-cultivation. It means we have different cells on either side of the fiber. We can place endothelial cells onto the insides of the fibers, where they will lay down flat when they're subjected to shear stress. They'll also form tight junctions and exhibit other physiologic traits. On the outside of the fiber, we have vascular smooth muscle. As we change the flow rate, as we change the shear on the endothelial cells, G protein formation and endothelial receptor expression in the vascular smooth muscle is directly affected. So something is being secreted by the endothelial cells that directly affects the physiology of the vascular smooth muscle. We can also take brain microvascular endothelial cells on the insides of the fiber and astroglial cells, and we can set up an active permeability barrier that behaves a lot like the blood-brain barrier in vitro. Here we have a nice micrograph of endothelial cells on the insides of the fiber after being subjected to 10 dynes per square centimeter shear stress for 24 hours. We're going to see our 0.1 micron pore size PVDF fiber. It always surprises me to see just how thin and flat this endothelial layer is on the insides of the fiber, recapitulating the in vivo situation for endothelial cells. If endothelial cells are not subject to shear, then they'll just continue to divide. Here, they'll sit there and form a monolayer and cease dividing. In this particular case, the researchers added circulating leukemic lymphocytes to the media circulating through the insides of the fiber and watched for their interaction with the endothelial cells. As it turned out, the CLLs would specifically interact with the endothelial cells, but only under conditions of chronic shear, where they would attach and then transmigrate through the fiber. This is a model for cancer metastasis, very significant findings. I believe the same mechanisms are in force for stem cell homing as well. It's a very, very interesting specific model, and the big advantage of using hollow fiber here is that we can collect enough cells from either the endothelial cells or the circulating leukemic lymphocytes and look at protein activation, receptor integration, and actually they've been able to elucidate the mechanism for cancer metastasis. This is an example of bone marrow stroma co-cultivation with hematopoietic stem cells. In this case, we utilized the 5 kD molecular weight cutoff fiber so that we could concentrate any of the secreted cytokines from the bone marrow and their influence on the hematopoietic stem cells. Researchers here found that hematopoietic stem cells expanded in the hollow fiber cartridge when engrafted 5 to 10 times more rapidly into nude mice than standard hematopoietic stem cells expanded in flask culture. More physiologic model for hematopoietic stem cell expansion. This is something I'm particularly proud to have participated in. Cryptosporidium is a single-celled parasite that infects the lower bowel of 40% of the children in Africa. It's a very complex disease with no known treatment. Until recently, it's not been possible to culture it in the laboratory in vitro. A couple of groups at Pace University and Tufts University Veterinary Medical School developed a way to culture Cryptosporidium in the hollow fiber bioreactor cartridge. Whenever we're looking to generate a new model, we need to look specifically at how the in vivo situation is portrayed, and then just try to recapitulate it in a hollow fiber system. In the gut model, it's an interesting situation because we have a high oxygen side, which is where the circulatory system is, and as it turns out, the inside of the gut is very low oxygen. So researchers were able to take gastric epithelium and utilizing oxygen scavengers in the extracapillary space, generate both a low oxygen and a high oxygen side, i.e. the circulating media through the insides of the fiber, and create this Cryptosporidium culture inside the hollow fiber bioreactor. They've been able to replicate all stages of development and are able to now utilize it through the help of the Gates Foundation for looking at drugs to eradicate Cryptosporidium. I do also just want to take this opportunity to mention that FiberCell Systems is an enabling supplier to NASA. So they utilize our cell culture cartridges in the International Space Station. This closed seal system with recirculating media is really going to be the only effective way that you can culture cells in 0G. Because you can't pour media, you can't pipette liquids in space. So we're proud of our association with NASA. When looking at complex biological systems, it's best to look at the in vivo configuration and try to recapitulate that as closely as possible in a three-dimensional hollow fiber bioreactor system. It was thought that placenta might be a good source of mesenchymal stem cells. So what we did was perfuse the placenta first with PBS to get rid of the blood and the cord blood and the hematopoietic stem cells. We weren't interested in them. And then we perfused it with collagenase for an hour. We just took all those cells, whatever came out, got rid of the red cells, and then seeded it into a 5 kD molecular weight cutoff hollow fiber bioreactor. We used the 5 kD so that we could enhance the effect of any secreted cytokines. We removed the non-adherent cells once a day, every day for 3 days, and then let the culture proceed for 7 to 10 days. As you can see, it's a 4-dimensional culture. We had time for these red nodules, 3-dimensional red nodules, to form on the surface of the fiber. And even more interestingly, we got a whole new batch of suspension cells that we could harvest from the cartridge being secreted by these red nodules. Suspension cells that are de novo being generated inside this hollow fiber bioreactor system. These rather small diameter suspension cells, when harvested from the hollow fiber bioreactor and placed into a T-flask with serum, quickly attach to the plastic and spread out, dividing rapidly. We can even see the formation of an embryoid body. If you're familiar with MSCs, you'll see that these look very familiar. Flow cytometry revealed that these small diameter suspension cells harvested from the extracapillary space of our Placental Co-Culture were phenotypically indistinct without any predominant characteristics. After these cells were cultured for 5 days in a T-flask with FBS, they reveal themselves to be 99% mesenchymal stem cell positive. These cells are either MSC precursors or true MSCs and reveal their characteristics only when cultured in flask with serum. Cell culture conditions have a profound effect in terms of the phenotype and behavior of cells. So in summary, hollow fiber bioreactors are the most in vivo-like method for the culturing of cells over long periods of time. Hollow fiber was 3D culture before the importance of 3D culture was recognized. Hollow fiber was cool before 3D was cool. It can be the only way to get 2 different cell types in close enough proximity at high enough density for long enough periods of time to observe interactions developing between the cells. 4D culture, enough time for cells to self-organize and for these interactions to develop. After starting with the 3D culture of Harrison and his plasma clots, cell culture then lost some of its physiological relevance through the use of 2D plastic flasks and fetal bovine serum. 3D hollow fiber bioreactors have evolved to be a 3D, more in vivo-like way to culture cells and provide the opportunity to more closely recapitulate complex biological processes. Please feel free to utilize the other resources on our website at www.fibercellsystems.com and also to check out some of the other webinars we have here on YouTube. Please feel free also to contact us with any questions you might have. Once again, I'm John Cadwell for FiberCell Systems. Thank you for your time.